Hi, once again, welcome to another video on PDEs. Now we have this problem here. This is section 13.5, I guess, in the textbook. And the problem number 9 to solve the Laplace equation. So Laplace equation is pretty much is solving for the temperature. If you have a rectangular plate, for example, you have a plate and you want to solve for the temperature U, and you have the boundary. For example, you have when this is X and this is Y. When X is 0 and Y is any number, which is here, you have 0 temperature, U equal to 0, which is this one. And when Y equal to X equal to 1, for any Y, here you have U equal to 0 also. And then for this one, you have for any X when Y equal to 0, you have U equal to 100, the temperature. And when for any X when Y equal to 1, which is here, you have U equal to 200. Right, so you want to solve how the temperature is going to behave, how it's going to change on the rectangular plate, how it's going to change. So you want to solve for the temperature U to see how it's going to change. So this problem, again, to solve, we are using separation of variables, again, the same method. So the only thing just to notice is, okay, you want to use separation of variables, but for that, you're gonna need boundary conditions, right, to solve for the constants. Usually, you just see, okay, you use the boundary conditions, the ones with value equal to 0. So these, I'm gonna use them when separating. And the rest, these other ones, I'm gonna use them at the end as initial conditions, right? To solve for the other when I have the Fourier series and stuff like that. So, okay, let's first separate. Okay, let's solution. Let's say U equal to X now times Y, because we have U function of X and U function of Y. There's no time here. Where you have X is some function just of X and Y some function just of Y. Okay, we have UX, X prime Y, and then we have U X double prime Y. Then we have delta U delta Y, Y prime. Then we have double Y prime, like that. Then I'm gonna sub to the original equation, then I get X double prime U Y plus X Y double prime equal to 0. Okay, now we have this. Now I just need to separate. Then I have X double prime Y will be equal to X minus X Y double prime. Then I'm gonna divide both sides by X Y. Then I have X Y and I have X Y. These both cancel. Then you have X double prime X is equal to minus Y double prime times Y. Then I'm gonna separate. I'm gonna say equal to lambda. From here, I have X double prime over X equal to lambda, and then Y double prime Y equal to minus lambda, right? Because there's a negative here. Then, if you isolate second derivative, minus lambda X equal to 0, then Y plus lambda Y equal to 0. Now I need to solve this problem for lambda positive, lambda equals 0, again the same procedure, right? So to solve for the constants that I'm gonna get, I'm gonna use here this as a boundary condition. I'm gonna use this. So that means this, and also if you look at this, it is just changing when x equal to 0 and x equal to 1, right? So that is telling me that actually the main equation that I'm gonna actually use to evaluate is the x equation. So, okay, case 1. Okay, I'm gonna say if lambda equal to 0. Then I have x equal to 0. The first integral, integrate one time is gonna be one constant, then twice. If I integrate second time, c1x plus c2. Okay, then from the boundary conditions, the first one is u x 0, no, wait, or 0 y equal to 0. So I have, let me just write again, 0 y equal to 0 is the same as x 0 for any y equal to 0. That implies that x 0 is just equal to 0. Then for the other condition, u 1 y equal to 0, doing the same thing, I just end up with x 1 equal to 0. So I'm going to use this to find c1 and c2. Okay, for x, when I put 0, c1 times 0 plus c2 has to be equal to 0. From here, c2 turns out to be 0. Now I'm going to use another condition, x1, c1 times 1 plus c2 has to be equal to 0. c2 is 0, so that just implies c1 equal to 0. Then x, which is c1x plus c2, is going to be just 0. As a result, ux, y, is going to be x times y is going to be just 0. So I don't have pretty much a solution here. Okay, now I'm going for the case 2. If lambda, I'm going to say, okay, if lambda negative, I'm going to say, okay, lambda equal to a negative number. In this case, if I put it here, I have x plus alpha squared x equal to 0. And I have y minus alpha squared y equal to 0. Okay, I just have, first I'm going to solve this here. This, as if I solve, the solution is, I'm going to say c3 cos alpha x plus c4 sine of alpha x, like that. Okay, x0 equal to 0 to find the constant c3 and c4. Then I get x0 equal to c3 cos alpha 0 plus c4 sine alpha 0 has to be equal to 0. Then I get c3 is just 0. Then I go for 1 has to be equal to 0. I have x1, c3 is just 0, so I have c4 sine of alpha times 1 has to be equal to 0. Okay, I don't want everything to be 0, then I just end up with 0. Then that means I'm going to say c alpha equal to 0 for c4 different than 0. Then let's say alpha equal to n pi. Alpha equal to n pi for n equal to 1, 2, 3, and so on. I don't want n to be 0 for the same reason as explained in the previous videos. So from here, you just have alpha equal to n pi. Then that means the solution equal to c4 sine alpha is n pi x for n equal to 1, 2, 3, and so on. So that means I'm gonna say for here uxy equal to x times y. I need to know so y. Then that means I'm gonna solve the second equation. The second equation okay, this is the second equation. To solve it, if you solve the characteristic equation, you get r equal to plus or minus alpha, like this. Then you're gonna write y equal to c, let me see, c4 c5 c3 c4. I'm gonna use c5 c6. It's gonna be c5 e alpha y plus c6 minus alpha y, or c5 hyperbolic cos of alpha y plus c6 hyperbolic sine of alpha y. Now the point is, which solution you're going to use? Okay, if we look at the boundary condition here, the plate is bounded, right? It's limited. We have a length from 0 to 1, and then from 0 to 1. Since the plate is limited, since the boundaries are limited, we're going to use this one. We won't use this one. So we have y c5 cos hyperbolic cos plus c6 hyperbolic sine y, like that. Now that's a solution. Then uxy is gonna be c4 sine of n pi x times c5 cos hyperbolic plus c6 sine hyperbolic sine, just okay, for n equal to 1, 2, 3, and so on. Okay, that's a solution for when lambda negative. Now, if you do lambda positive, that means you'd have to end up with a hyperbolic cosine and sine for x. Then when you evaluate, this is just one of those cases where you're just gonna end up with 0. So I won't do that. You can just do that as a practice, but you don't have to do that. Usually when you end up with cos, as if you watch my videos, pretty much you already know that when you end up with hyperbolic cos and you evaluate it for boundary conditions, the solution is just 0. They don't lead you to significant solution. So from here, I can just write the general solution, summation n equal to 1 infinity c4 times c5. I'm gonna say, okay, it's gonna be one constant, hyperbolic cosine, plus c4 times c6 is gonna be just another constant for hyperbolic sine times sine n pi x for n equal to 1, 2. Oh no, here don't need, because you are already summing them. Since you are summing them, you don't need, you can just stop here. Okay, now you need to find these constants. So how do you find these constants? Then you turn to the other boundary conditions. You're gonna use them as initial conditions, but they're actually boundary conditions. So you're gonna use them. Now you have two. You have u x. Let me just, okay. You have u x0 equal to 100, and then you have u and x1 200. Okay, I'm gonna use the first one, y0 summation n1 infinity. I have an y0 hyperbolic cos. I'm gonna just write this way. I don't want to write all thing. plus bn hyperbolic 0 sine of n pi x has to be equal to 100. This is 1, so you just end up summation n1 to infinity an. This is 0, so just end up sine of n pi x equal to 100. Then from Fourier series of sine is 2 over the length. The length, if you go to the plate, from 0 to 1, so your length is just 1. Integral 0 to 1. The function fx is 100 sine of n pi x dx. Okay, then an equal to 2, 0 to 1, 100 sine n pi x dn pi x over n pi, like that. Then you have 200 over n pi. Then you have this integral here. Sine x dx is just minus cos of n pi x. Like that. Then you have from 0 to 1. Then you're going to have, when you evaluate, you get 200 over n pi. I'm going to put minus here. You have cos of n pi minus 1. When you plug 0, just get it to 1. Then you have an. You have 200 n pi 1 minus cos of n pi. 200 of n pi 1 minus 1 over n. That is for cos of n pi equal to minus 1 over n. Minus 1 to the power of n. Okay, that's your an. Now you need to find also the bn. I'm going to use the other condition. U x1 summation to infinity. Then you come here, you have an, right? You have an hyperbolic cos alpha 1 plus bn hyperbolic sine of alpha 1 also times sine n pi x has to be equal to 200. Okay, now all of this is going to be a constant. I'm going to say equal to Cn. Then just mean you have summation. That's a constant because this is alpha, this is alpha, this is an, so all of them are constants. So you just want to find the value of this general constant in this case. Cn sine n pi x has to be equal to 200. From Fourier, 2 over the length, 0 until the length, then you have sine n pi x dx. Okay, 200 here. It's 200 because this is the function. This is the function, fx for the formula. Then you have Cn equal to 400, 0 to n, sine of n pi x dn pi x divided by n pi. Then I have 400 over n pi, integral 0 to 1. I have sine n pi x dn pi x. From here, I have Cn equal to 400 dividing n pi minus cos of n pi x. This is just the same as the previous that we did for an, so you can just go straight. It's gonna be 400 over n pi 1 minus 1 to the power of n. Now Cn equal to an hyperbolic cos of alpha plus Bn hyperbolic sine of alpha. And I want to solve for Bn. Bn hyperbolic sine of alpha has to be equal to 400 n pi times 1 minus 1 to the power n minus an. What is an? We solved the an. An is 200 n pi, right? Yeah, n pi 1 minus 1 to the power of n. Yeah, we're just getting cos hyperbolic of alpha. Then from here, you can just isolate Bn. Bn 1 over hyperbolic sine alpha times, what I'm gonna do, I'm gonna factorization n pi, then I end up, okay, these are also the same, so I can just do 1 minus 1 n over n pi. Yeah, then I just end up, I'm left with 2. Yeah, let me see, 2 minus cos, hyperbolic cos of alpha. Then Bn equal, just to organize, you have 200 over n pi times 1 minus 1 to the power n over sine, hyperbolic sine alpha 2 minus cos alpha. That's what Bn. Then you just need to sub them there just to write the equation. Get u xy equal to an. If you look at an, you have 200 over n pi, 200 over n pi. So you can take out 200 over pi summation n1 infinity. Then you have an. You are left with 1 minus 1 over n hyperbolic, let me see, cos, yeah, cos hyperbolic, yeah, let me see, cos alpha y plus Bn, you remove this and the pi, and you are left with 1 minus 1 to the power n over hyperbolic sine alpha times 2 minus cos hyperbolic, yeah, like that, divided by n times sine hyperbolic sine alpha y, and all of that has to multiply sine n pi x. So this is the general solution. So you can just use this solution to plot using MATLAB, and then you're gonna actually see how the temperature is gonna change from, since it is 100 here to 100 here, how the temperature is gonna behave inside this body, how they actually is gonna behave. So you can use this result, and you can use MATLAB to do some coding and interpret this solution. So that's the solution for this particular problem.